The lesson for today is the real number system, objectives to identify numbers in the real number system, and to solve equations by finding square roots. Let's consider this example. When investigating an accident, police officers often need to determine how fast a car was traveling before it skidded to a stop. They use the formula S equals radical 30 df, where S is the speed in miles per hour and d is the length of the skid marks in feet. And F is the coefficient of friction. What was the approximate speed of the car if the skid marks are 80 feet long and the coefficient of friction is estimated to be 1.2? Okay, now what is the coefficient of friction? We don't need to know this, but I'll tell you anyway. Okay, so the coefficient of friction is the ratio of the force that maintains contact between an object and a surface and the frictional force that resists the motion of the object. Okay, so that is all technical, and we don't need to know that now, but that is the definition of the coefficient of friction. Okay, that's the formula how to find the coefficient of friction. Okay, so we go back to our problem. S equals radical 30 d times f. Substitute the values 80 and the coefficient of friction is 1.2. 80 is 80 feet long, the length of the skid mark. So it becomes radical 2880. Using a calculator, you end up with this number, and the car was traveling at about 54 miles per hour. That's how they find out how fast the car was traveling. Okay, if and also how to determine if a car is at fault or not. That's one way of determining that. Okay, move on to the next one, which brings us to our concept. Our concept is irrational numbers. But before we talk about irrational numbers and rational numbers, we need to go back and recall what rational numbers are. Okay, rational numbers in 5-1, lesson 5-1, are numbers that can be expressed in the form of a over b, when a and b are integers and b is not equal to 0. Okay, again, rational numbers are numbers that can be expressed in the form of a over b or as a fraction. Okay, where b is not equal to 0. Why not equal to 0? Going back to commandment, the first rule of commandment in math, thou shalt not divide by 0, which simply means that if you divide by 0, the number will become undefined. Okay, so rational numbers can be always expressed as decimals because they can be expressed as a over b that terminate or repeat. So when you talk about decimals that terminate or repeat, they're both rational numbers. Okay, for example, 7, 1/3, negative 4.9 are rationals. Okay, the number 2880, which is 53.66563,146, is not a repeating or a terminating decimal. If you notice, look at the decimals after 53. Okay, look at the digits after the decimal of 53. It will not give you a pattern. It will neither repeat nor will it terminate. The 3 dots indicate that it repeats forever. Sorry, it goes on forever. Okay, it does not repeat forever. It goes on forever. Okay, this kind of number is called an irrational number. Okay, so let's define what an irrational number is. An irrational number is a number that cannot be expressed as a over b, where a and b are integers and b does not equal to 0. Okay. Other examples of irrational numbers are shown below. Radical 3, 1.3720508. The 3 dots indicate that it will go on forever, not repeat. And the most popular rational number that we all know is what we call pi. Okay, 3.14159. Okay, and so on and so forth. It will not terminate or nor will it repeat. It just goes on forever. So these are two good examples of irrational numbers. Okay, now let's look at example number 1. Let's determine whether each number is rational or irrational. If you notice 0.222, okay, there is a pattern. The number 2 repeats, so the 3 dots mean that 2's keep repeating. This is a repeating decimal. And we know if it's a repeating decimal, it can be expressed as a fraction 2 over 9. Thus, this is a rational number. Letter B, 0.35, okay, it terminates, it stops at 5, okay, which simply means that it can be expressed as 35 over 100 or 7 over 20, A over B. It is also a rational number, okay. The last example, C, if you notice, there is no pattern, okay. Well, there is 5222, 5222, okay. It creates a pattern, therefore it repeats. This part of the decimal repeats. No, actually it does not, because if you look closely, you have 52, then 5222, then 3 twos after that, and 4 twos after that. So there is no repeating pattern, okay, in terms of the digits. Okay, the repeating pattern means that all the digits that repeat need to be the same every single time. So in this case, okay, it does not repeat nor terminate and is therefore an irrational number. It does not have a pattern to it, but since fives are separated by increasing numbers of 2, there is no exact repetition. Like what I said. The book only says it better. Okay. The set of rational numbers and the set of irrational numbers together make up the set of real numbers. Okay. Venn diagram at the right shows the relationships among whole numbers, integers, rational numbers, irrational numbers, and real numbers. Okay. So when you talk about the set of real numbers, let's first look at the set of whole numbers. This now becomes the set of whole numbers. Okay, so you have whole numbers 0, 1, 2, 3, 4, 5, 6, 100, 150. Those are all examples of the set of whole numbers. Okay, and remember the definition. Okay, when we go higher in this hierarchy of numbers, okay, the next circle that we are going to draw will be the set of integers, which simply means this: all whole numbers are integers. How did we define integers before? The set of integers is the set of whole numbers and their opposites, including 0. So the set of integers will include negative numbers. Okay, whole numbers will include 1, and negative 1 is the opposite of negative. Negative 1 is the opposite of 1. So negative 1 is an integer, but negative 1 is not a whole number. So which simply states that all whole numbers are integers, but not all integers, or but not all integers are whole numbers. Okay, a good example would be negative 3. It is an integer, but it's not a whole number. Okay, 0, it's a whole number, and at the same time it's an integer. Okay, but if I say negative 62, okay, that is an integer, but it's not a whole number. Okay, moving on. So after we have that, we make this bigger. Okay, so now we have the set of rational numbers. So in the set of rational numbers, you have integers and whole numbers. What does this mean? It simply means that all whole numbers are rational numbers, all integers are rational numbers, but not all rational numbers are integers, okay? And not all rational numbers are whole numbers. Let me give you an example. A good example would be, this would be negative 1/2. Negative 1/2 is a rational number, but it's not an integer, nor is it a whole number, okay? Another example is 0.2. It's a rational number, okay, because it can be expressed in the form of A over B, but it's not an integer, nor is it a whole number, okay? And the last part of our puzzle would be the set of irrational numbers. Irrational numbers are numbers that are not rational numbers, and a good example would be radical 2. If you get the square root of 2, it will neither terminate nor will it repeat. Another good example, which was given earlier, pi, 3.141592, so dot dot dot. Okay, will neither repeat nor will it terminate. Another good example is radical 5. If you notice a set of irrational numbers, okay, are radical expressions wherein the radicand or the number inside the radical sign is not a perfect square. Okay, because if we say radical, okay, negative radical 4, that is an integer. Why? Because square root of 4 is 2, and we simply put the negative sign. This is negative 2. So it is an integer. Okay? Radical 9 is a whole number. Why is that? Because radical 9, or the square root of 9, is 3. And 3 is a whole number, it is an integer, and it is a rational number. So all the numbers in the set of irrational numbers, okay, have radicands that are not perfect squares. And if you combine the set of rational numbers and the set of irrational numbers, both of them now are called the set of real numbers. Okay, so these two rectangles form the set of real numbers. Okay, why are they real numbers? Because later on in high school you will learn that there are such things as imaginary numbers. Okay, but we'll not concern ourselves with that right now. The following chart shows the sets of numbers to which several numbers belong. Negative 9, it's an integer, therefore it's a rational number and it's a real number. Radical 35. 35 is not a perfect square, therefore it's not a whole number, it's not an integer, it's not rational, but it's an irrational number and still a real number. Radical 49, or the square root of 49, is 7. 7 is a whole number, an integer, a rational number, and a real number. Okay, 0.5858, it's a repeating decimal. If it's a repeating decimal, it's a rational number and real number. 0.12, 123, neither repeats nor terminates. That's an irrational number and a real number. And again, 9, it's a whole number, integer, rational, and real. Okay? Now let's do this. The equations you have encountered so far have had rational number solutions. Some equations have irrational number solutions. You can solve some equations that involve squares by taking the square root of each side. Let's consider this example. Solve each equation, round decimal answers to the nearest tenth. X squared equals 81. Okay? To be able to solve this equation, to be able to get rid of the exponent 2, we need to square both sides of our equation. So x squared equals 81. Okay, we square both sides, and that was shown there. Okay, and what happens is that you get now, after you square x squared, we're left with x equals the square root of 81, or x equals negative 81. Why is that? Because there are two values of x which will give you 81. What are these two values? 9 and negative 9, just like what you have here. Okay, because if you square 9, it will be 81. If you square negative 9, it will be still 81. Remember, negative 9 times negative 1, 9. Okay, like signs make a positive product. So your solution checks out. 9 squared is 81, negative 9 squared is 81. We've just checked our answer to be correct. Okay, next example, y squared equals 75. Okay, we get the square root of y squared, we get the square root of 75, and this is how the process goes. Okay, we square both sides, end up with y equals 75, or y equals negative radical 75. Okay, which gives you a value of 8.66025438 to the nearest tenth. Is approximately 8.7 or negative 8.7. Okay, let's move on. And let's move on to this example, a real-life example, how radicals are used. The voltage V in circuit is given by the formula V equals radical PR. And this formula V is in volts, P is the power in watts, and R is the resistance in ohms. Okay, if you know an electrician, this is what they deal with on a daily basis. So an electrician has a circuit that produces 1500 watts of power. She wants the voltage in the circuit to be no more than 110 volts. Should she design a circuit with a resistance of 7.5 ohms or 7.8 ohms? Okay, this is a question we want to answer. We want to find out if the circuit needs to be 7.5 or 7.8 ohms. Okay, this is what we know. For the circuit, P equals 1500, V equals 110. To determine which resistance to use, you can use the calculator. You can use the calculator to evaluate. You can use the calculator to evaluate radical 1500R for R equals 7.5 and for R equals 7.8 to find out which one will produce no more than 110 volts. Okay, so we evaluate first 1500R and we replace R with 7.5, end up with 106.060172, and we use 7.8 for R. End up with this number 108.1665383. Okay, so she can design the circuit with either resistance if she wants the voltage in the circuit to be as close to 110 volts. Then she probably would want the resistance to be 7.8 ohms because this is the one closest to 110. Okay, and that's the lesson. Summary, question, you know the drill. Thank you.